Hello, welcome to this lesson of our study of what I mean by eigenvalues and eigenfunctions. Okay, so this will help us solve some PDEs or partial differential equations. You can also apply it in integral equations and a whole lot of ways to solve some math problems. Okay, so in this particular lesson we are going to look at the eigenvalues and eigenfunctions of a PDE of the second order form. Okay, so we are restricting ourselves to the second order, and if by chance we get to any general form, then we will do. Okay, but then the explanation I'll give you will be able to guide you in terms of solving other questions or similar questions in the higher orders. Okay, so when we talk about eigenvalues and eigenfunctions, okay, let me open a page for you to understand. When we say the eigenvalues, okay, of a function, when you talk of the eigenvalue of a function, if you have a function, let's say like we did, we've written in the first page, okay, like we've written in the first page, you see we have y prime prime or something like that. My pen is not coming. Okay, have y prime prime or something like that. Okay, plus some lambda y equals some 0. Okay, or something like that. Now what this means is that the eigenvalue for this function are the values of lambda, for which when I substitute here, I will not get the trivial solution y of x. We assume that this is a function of x, so y of x is equal to 0. This is actually a solution to all differential equations. Okay, the trivial solution is a solution to this second order second order ODE. But we don't want this because this is trivially known. We know it already. So we want the solutions, or we want the values of this lambda that would not give us the trivial solution. The values of lambda which when we put here after solving this differential equation and using the boundary conditions, we won't get 0. So those are what we call the eigenvalues. And then the corresponding functions that will give are what we call the eigenfunctions. I hope you get my point. Okay, so the eigenvalues are related to this lambda here, and then the eigenfunctions are the corresponding function for each lambda. So let's say if I have lambda 1 equals, let's say 2, and after solving I get a solution for this function, then that function will be the eigenfunction for the eigenvalue 2. I hope you get the point. Alright, so let's go back and start. Remember, the eigenvalues and eigenfunctions are also related to boundary value condition or boundary value problems. Okay, when you talk of boundary value problem, it's just an ODE given, and then or a PDE, it can be any of the form, and then the function is defined. Yes, we have the functional value at some boundary. Okay, the boundary means that the points where the function is defined are not the same. Okay, so here y of 0 here is different from y of 2 pi. Okay, so you could see that it's just a boundary like that, 0 to 2 pi. So this is the boundary we are talking about. And also the boundary values are homogeneous, meaning their functional value there are 0, 0 like that. Okay, so just take note of all these before you start solving. Alright, so after explaining these steps, let's try to get to the working. Okay, so to solve this, we have an eigenvalue problem here. Okay, that looks like this. We have an eigenvalue problem here, that is y prime prime plus lambda y equals 0 with the subjected boundary conditions given as y of 0 equals 0 and then y of 2 pi equals 0. So with this, how we solve this is that we just consider the ODE given, solve it as we know for how to solve ODE. So y prime prime, my pen is not working. Okay, plus lambda y equals 0. So to solve this ODE, we assume, since this has the lambda here is a constant, okay, so we have constant coefficients equation or second order equation. So with this, we said that there's a solution that we can assume that will satisfy this, that we should assume that y is equal to e to the power rx. I'm showing you how we got those form. Okay, so after assuming this, then this should satisfy the equation. So we are saying that therefore y prime, let me differentiate it 2 times, will be r squared e to the power rx. Okay, now if you go through the systematic differentiation, you get this. The first y prime is r e to the power rx. Okay, you know how to differentiate exponential functions, so you go through that to get the second order differential, or some y prime prime. Okay, after getting your y prime prime, you substitute your y prime prime and your y, this is your y prime prime and this is your y, back into the differential equation. Okay, so y prime prime is actually r squared, wherever you see y prime prime, you put r squared there, r squared e to the power rx. Okay, this is what we had, plus lambda y, and the y here is the y of x. Okay, and this should be equal to 0. And now you can see that e to the power rx is here and is here, so we can factor that one out. Rx e to the power rx, then into r squared plus lambda should give you 0. Now we have the product of two things. If I have a product of a b being equal to 0, then it's either a is equal to 0 and b is not equal to 0, or b is equal to 0 and a is not equal to 0, or both are equal to 0. Okay, so in all the 3 cases, when both are 0, their product will give you 0. If a is 0 and b is not 0, 0 times b will still give you 0, and if b is 0 and a is not 0, you still get 0 as well. Okay, so in these 3 scenarios, you still get 0. But then the question is, this is our function e to the power rx. If it should be equal to 0, then we'll have y of x. You are saying that e to the power rx is our solution. Okay, so if that one should be equal to 0, then we'll have y of x equals 0. Okay, so we have product of this and this. Which one is 0? Which one of them is 0? That's the question we are asking ourselves. Okay, so if y of or if e to the power rx is supposed to be equal to 0, then it means y of x is actually equal to 0, which is the trivial solution that we don't want. Okay, so here it means that we can't, let me erase this for you. It means that we can't actually say that e to the power rs is 0. Then the only case we can consider is when this other side, that's r squared plus lambda, should be equal to 0. So r squared, okay, plus lambda should be equal to 0. And in that case, we solve for lambda and we see that r squared is actually equal to minus lambda, or you solve for r. Okay, this will imply that our r is equal to plus or minus the square root of minus lambda. Okay, so now this is our solution for the r. Now the case is lambda greater than or equal to 0, or is lambda greater than 0 only, or is lambda equal to 0 only, or is lambda less than 0 only? So this is the case we should consider. We'll consider 3 cases. Okay, so the first case, case 1, is when or if, okay, is if or when lambda is greater than 0. When lambda is greater than 0, it means that lambda is positive, and negative lambda, or the negation of lambda, is actually negative. So the square root of that will simply, it means that our r will be equal to, in this case, will be equal to plus or minus the square root of minus lambda, and this is equal to plus or minus the square root of lambda times square root of -1. Okay, I know you know this, but then let's go through that. Okay, and the square root of -1 is actually I, a complex number, so I have plus or minus square root of lambda then I hope you get this point. And now I have 2 distinct roots which are complex roots. Okay, and we are saying that once you have a complex root, then the solution can be written as, or this is the idea. Let me write it here before I convert it to the sine and cosine. So once you have 2 distinct roots, we said our solution y of x is equal to e to the power rx. So once you have 2 roots, that is r1 and r2, that is the plus and minus. Okay, so you have r1, 2, you can put them here. You can also put them here, r1, 2. The reason is we had r squared, and when you have a squared something after solving, you're supposed to get two solutions, okay, because of the square here. So we have two solutions for our r, and that our solutions should be like y of s is equal to e to the power, or a constant a, e to the power r1x plus a constant b, e to the power r2x. Actually, this is how it goes for all of them, okay, all of the kind of solution you get. But when it is complex, then e to the power something I can be converted to complex, or can be converted using the polar coordinates to convert them to the sine and cosine, okay. So you can go and search or read on that as well, but then here I'll just convert them straight away for you. So since our r1 is given by, or r1 and r2 is given by square root of lambda I, that is plus or minus, then our y of x, after putting it there in the exponential and converting it to complex, we will have something like a cos of square root of lambda x plus b sine of square root of lambda x. And remember, this is only under the case 1, okay, but it is being defined at a boundary that y of 0 is equal to 0. So let's quickly do that. And y of 0 will be equal to a, the cos of 0, because you have the whole of this cos of lambda x, they're all together, okay, like this. So now I put x equals 0 inside this, I'll get cos of 0, and that will be just 1. So I have a plus sine of 0, and that is 0. And you are seeing that after simplifying, this should be equal to 0. This implies that what our a is equal to 0. The a is equal to 0 is coming from this equation. You solve this and you see that a is equal to 0. You have a plus 0 equals 0. So you make a the subject, you have 0 as well. Now this implies that our y of s is actually equal to, since a is 0, y will just tend to be b sine of square root of lambda x, because the a is 0, so we have only this side. Now you consider the other boundary condition, y of 2 pi, and y of 2 pi is equal to b sine of 2 pi square root of lambda. Now remember, the s is just multiplying the square root of lambda, so you can interchange them anyhow, okay. So once you have this, the question is, they are saying that, or the question is given that this should be equal to 0, okay, and this should be equal to 0 means that I have b times sine of 2 pi square root of lambda, and this should be equal to 0. This means either b is equal to 0, and then sine of 2 pi lambda, or square root of lambda, is not equal to 0, or, okay, b is not 0, okay, I have the product of two steps giving me 0, and then sine of square root of, or 2 pi square root of lambda is equal to 0. So which one of these, or both are 0, okay, or both of them are 0, and in all the three cases this should give us 0, because if b is 0, then b multiplying this will give me 0, and if sine of 2 pi square root of lambda is 0, then b multiplying that will also give me 0, and then if all of them are 0s, then it means that their product will still give me 0. I hope you understand this. Now this is the case. If b is equal to 0, then it means that the equation y of s, or the solution, has turned to 0, because it has turned to b sine of this. This is what we had for y of x, okay. So if b is 0, then we have y of 0, or y of s equals 0, which is the trivial solution. I hope you get the point, okay. We are using the b is 0 from this part. If b is equal to 0, then it means if you put the b back in the y of s, we still have a trivial solution. Now let's consider the other case where the sine of 2 pi root of lambda is equal to 0. If that is the case, then it means we are just supposed to find the value of lambda, okay. And remember, here there is an x here, so when I put the value of lambda here, the equation wouldn't be 0. So it means it's actually the first case will not exist. That's the b equals 0, and this one is not equal. The sine of 2 pi square root of lambda is not equal to 0. That one wouldn't work. So we have to consider the case where the b is not 0, and then the sine of 2 pi square root of lambda is actually 0. I hope you get the point. After this, I'll give you a trial question to try on your own, and I hope you'll be able to do that. So this means that this thing, sine of 2 pi square root of lambda is rather equal to 0, and the b is not equal to 0. If that is the case, then 2 pi square root of lambda should be equal to sine inverse of 0. Now remember this. The sine inverse of 0, when you punch it on your calculator, will actually give you 0. But then if you consider the sine graph, okay, you realize that it is actually equal to n pi, where n is integer multiples, okay. Now if you include sine inverse of 0 is actually equal to 0, like I said on your calculator, but then the n is just integer multiples starting from plus or minus, okay. I hope you understand. But we've already said that lambda is greater than 0, so the minus aspect shouldn't come. You should only consider the plus aspect, okay, the positive aspect. Now remember, if n equals, if you start, let me put it here, the sine inverse of 0 is actually 0, but then I said the sine inverse, let me explain something small here. The sine inverse here that you see of 0 means that you should find corresponding angles, okay, that their sine of those angles we don't know should give you 0, okay, and then those are the n pi, n integer multiple of pi, where n starts from 0. Okay, so when you put n equals 0, you have 0. So sine of 0 will give you 0, meaning that sine inverse of 0 is also 0. Then we put n equals 1. The sine of pi, you can try that on your calculator using your calculator in the radians mode, or you can convert the pi to the degree mode, that is the 180 degrees, and find sine of 180, and that will still give you 0. Sine of 2 pi, which is the 360 degrees, will also give you 0, meaning that the sine inverse of 0 is actually, we have a set of values for that, okay. So the set of values is just n pi, where n starts from 0. This is the argument here, so that you don't get confused, okay, because when you punch it on your calculator, you're actually going to get 0. You can get n pi. So this is the idea behind it, okay. So n pi, but if n is supposed to start from 0, okay, if n, and I said n is an integer multiple, but then we are taking the positive part because we said lambda is actually positive, it's greater than 0, so the negative part wouldn't work. So n equals 0, 1, 2, and the rest. But if you consider 0, then it means we'll put 0 here and we'll have everything after solving. We'll have lambda equals 0, but I said lambda is actually greater than 0, so it means n shouldn't be equal to 0, or n shouldn't start from 0. So for this case, n should be equal to 1, 2, 3, and the rest, okay. I hope you understand the argument here. So it means my square root of lambda should be equal to, after dividing through by 2 pi on both sides, divide here by 2 pi, divide here by 2 pi, so that this will cancel this, and this here pi will take pi away, so I'll have n over 2. This implies that my lambda will actually be equal to n squared over 2, or sorry, over 4. I have to square both sides. That's my lambda, okay. And in this case, this shows that n, we said n is equal to 1, 2 going, that is the integer, positive integers, okay. Now we have lambda equals n squared over 4, okay. You have to just go ahead and write our function. Our function y of x is equal to b sine of square root of lambda x, okay. And b, we said, is not equal to 0, meaning that this function, or this solution actually has infinitely many solutions because of the b, okay. And even the lambda here is many. B sine of, then square root of lambda is n squared over 4. The square root will give me what? N over 2. Oh sorry, yes, n over 2. x. So this is my solution. Now the question is, we are supposed to find the eigenvalues and eigenfunctions of that. And the eigenvalues, remember I said they are the values of lambda. So the eigenvalues, lambda n is actually equal to n squared over 4 with your n equal to 1, 2 going. That is 1, 2, 3, 4, the rest, okay? And your eigenfunction, yn of x. Now when writing the eigenfunctions, take the constant b, or the constant in whatever question you solve, to be 1, and that writes the remaining functions you have. So n over 2x, comma, then n equals 1, 2, 3, and the rest. Okay, so this is the solution for the case 1. When you consider case 1 where lambda is actually greater than 0. Okay, so with this case, that is what you have. So for case 1, the eigenvalues are just lambda n equals that, and the eigenfunctions or corresponding eigenfunction is this one. Okay, now you consider another case we just finished right now. Case 2 is when lambda is actually equal to 0. When lambda is equal to 0, then our R12, which we said is plus or minus square root of minus lambda, is actually equal to square root of 0, and that is 0. So here we have a repeated root because R1 and 2 are both zeros, meaning that our solution, I'm just writing the solution back, and I will urge you to go and find why we have something like this. I've already explained this in solving one of the PD's videos, okay? Or let me just go through it, okay? I don't want to get you confused. So I have this a e to the power r1x plus b e to the power r2x. Okay, but if you put r1 and r2 here, they are both 0, so realize that the term a and b will be the same, so you have to add an x here, so it becomes bx e to the power r2x. Okay, so when I put my r1, which is 0, inside, I have e to the power 0, which is 1, so I have a plus bx, then e to the power 0. The r2 is also 0, e to the power 0 is 1, so I have only this. So for repeated root, this is why you always write that the solution is a plus bs. Okay, so with this, we said y of 0, you apply the boundary conditions here, is equal to 0, implies that a plus b times 0, and that will be 0, should give you 0, and this will imply that a is actually equal to 0, meaning my y of x has tended to be equal to bx. Also, with the other boundary condition, we said that y of 2 pi should be equal to 0, meaning y of 2 pi is equal to, using this case, it will be equal to 2 pi b. Okay, because we have bx, so we have, when we put 2 pi to be equal to x, we have 2 pi b, and that is equal to 0. And now you have a number multiplying b. Okay, this is not an expression, this is a number, meaning that b is equal to 0 over 2 pi, which is 0. So with here, our y of x is also equal to 0 because we don't have any other case to consider or any other thing to consider. Using the boundary conditions, we've gotten the trivial solution, meaning that for case 2, we don't have any eigenvalue or eigenfunction. We don't have any eigenvalue, okay? Because only the trivial solution exists, okay? We have no eigenvalues and eigenfunctions for this. Now we consider another case 3, okay? So case 3. With this case, you see we've considered lambda. The first case was lambda greater than 0, and the second is lambda equals 0. So the third case will obviously be lambda when lambda is less than 0. And if lambda is less than 0, then this is what you do. If lambda is less than 0, now r12, which is equal to plus or minus square root of minus lambda. Lambda is already negative because it's less than 0. Okay, so the minus of lambda will be a positive number, let's say k. So let me call this plus or minus square root of k, and so it's a positive number. So our solution, y of x, will then be equal to a1 or a e to the power positive k x plus b because you have plus and minus. So the first one is just positive and second is negative. E to the power negative square root of k x. So they are both positive and negative, right? But in solutions to ODEs, when you have this kind of solution, we can convert them to cosh and sinh. Okay, but if you want to still work with this, you can actually work with this. But the reason why I want to convert it to cosh and sine is because of the angle in it. Okay, so when you have this, don't panic. This is very simple. This is the same thing as having plus and minus complex numbers. When you have this one, it's plus or minus real numbers, and you can convert them to a cosh square root of k x plus b sinh square root of k x. So whenever you are solving ODE problems or solving any problem, you have this distinct roots which are just opposite to each other. Remember, the distinct roots are just plus or minus. They are not different values. I hope you understand what I'm trying to say. If you have different values like 2 and 3, or let's say we've gotten something like root k and root t, that would have been different, and we would have maintained them like this. But once you have distinct roots which are just opposite in sign, then you can use a cosh and sinh. Okay. Alright, so with this, y of 0 is actually equal to 0, so implies that if you have put y of 0, that is x equals 0 in this, I'll have a cosh 0 plus b sinh 0, and sinh 0 is 0, cosh 0 is actually 1, so you have a plus 0 equals 0. This will imply that a is equal to 0, so we are done with the a, and our final function returns to y of x equals b sinh root of k x. Okay, so you consider the other case where we said y of 2 pi is actually equal to 0, meaning that y of 2 pi for this part will be equal to b sinh 2 pi square root of k. Okay, and that we are saying that this should be equal to 0. But then let's consider this. We are saying that lambda is actually less than 0. Okay, lambda is actually less than 0, so it means that this 2 pi root of k will never be equal to 0, and the sinh of 0 is only when you get 0. I hope you get this point. When you have sinh of 0 is equal to 0. Okay, now this part, you are saying that lambda is less than 0, and that minus lambda will be a positive something, and then when it's less than 0, it's never equal to 0. And so this bracket here, that is a 2 pi square root of k, would never be equal to 0, meaning this part sinh of 2 pi k or square root of k will never be equal to 0, because the sinh of 0 is only when you have 0 here, that's what you get, sinh of 0, and that's the only thing we'll get 0. But then that part is also not equal to 0, because we've already declared that lambda is less than 0, meaning the square root of k here is never equal to 0, and then we won't have a 0 in the sinh argument, meaning that part wouldn't be 0. So, but we have that b sinh 2 pi square root of k is actually equal to 0. The product of these two is giving me 0, but then already you've said that this will never be equal to 0, meaning the only thing that will make this 0 is b equals 0. That is when you multiply, you get 0. This shows that when b is also equal to 0, we have our function y of x being equal to 0. And that is the only thing we can say here. Meaning the case 3 has also yielded the trivial solution y of x equals 0, meaning that we have no eigenvalues, and for that matter we don't have any eigenfunctions as well, since we have only the trivial solution here. So with the question that was solved, that is a y prime prime plus lambda y equals 0, with the boundary conditions, this y of 2 pi equals 0, the eigenvalues, the only eigenvalues here is that we have the eigenvalues lambda n equals n squared over 4, where n is equal to 1, 2, 3, and the rest, with the corresponding eigenfunctions yn of x being equal to, I said that for that you have to take your constant b to be equal to 1, sine of n over 2x, with n being equal to 1, 2, 3, and the rest. Okay, so these are what we call the eigenfunctions and eigenvalues of this corresponding question. We had to, initially I was planning to go through this, find all the eigenvalues and corresponding eigenfunctions of the B.V.P. This one the same question, but here the boundary conditions are in terms of derivative. That is, the y prime of 0 is equal to 0, y prime of 2 pi is actually equal to 0 as well. So with this particular question, I will just show you the way and tell you the eigenvalues and eigenfunctions you get, but then I may not go through it with you, so I will leave the working aspects for you to go and do, and then you tell me in the comment section that you're able to do or not. Okay, so let's actually look at the solution. The solution for this, we've already solved this. Okay, going through that same thing, you have our R12 will be equal to, if you remember the first question, that is, we said is equal to plus or minus square root of lambda minus lambda. And so if the case 1, you have to do the same case as case 1. That is, if lambda is less than or greater than 0, let me put it that way, then our solution will be in terms of complex roots. Okay, because you have a square root of a negative number. So our y of x will then turn to a cos, I want you to go through the working aspects, a cos of square root of lambda, then x plus b sine of square root of lambda, then x. Okay, then you apply the boundary conditions. The boundary conditions are defined at y prime, so it means you have to find y prime of x using this case, and that is equal to minus a square root of lambda sine of square root of lambda x plus b square root of lambda cos of square root of lambda x. That's the derivative you have. So y prime of 0 will then be equal to b square root of lambda. I hope you get this point. B square root of lambda, because sine of 0 will give you 0, and then cos of 0 will give you just 1. And you're saying this should give you 0. And for that matter, for here, if I divide through by square root of lambda, my b will be equal to 0. Now go to y prime of 2 pi, and that is equal to, remember, b is actually 0, so it means my y prime of x has then turned to minus a square root of lambda sine of square root of lambda x. So my y prime of 2 pi will then be equal to minus a square root of lambda sine of 2 pi square root of lambda equals 0. We are saying that this is equal to 0. Now, if a should be equal to 0, or we can pick this whole equation, divide through by square root of lambda. So I have minus a square root of lambda here. Okay, then sine of 2 pi square root of lambda equals 0. Now, if I divide through by square root of lambda, this side will go, and 0 over 8 will give you 0. Okay, so we have a sine of 2 pi square root of lambda equals 0. And now, if a should be equal to 0, then you definitely have the trivial solution. But you don't want that, okay? You are seeing that lambda is supposed to be greater than 0. I hope you get the point. Lambda is supposed to be greater than 0. And that's the same argument works here. That if a is supposed to be equal to 0, then we have a situation whereby, how do I call this? The only solution we'll get here is a trivial solution. Okay, so we'll have to put sine of 2 pi square root of x equals 0. Now, let me just say this again. In the first question, we got to a point where we had the signs, and I said that the signs part wouldn't be equal to 0. Yes, we had the same argument there, but then I talked about the signs, saying that the signs is only 0 at the point where you have the argument inside the signs being 0. This is what I mean. The signs, I don't want to confuse you, it's only 0 if here is 0. Okay, but then we already told you that lambda was actually less than 0 and that it wouldn't be 0 there. So here there wouldn't be any 0 for that matter. But let's come back to the sign. The sign can be 0 at multiple or integer multiple of pi. Okay, so it's not only 0. So here, even if lambda is greater than 0, that is meaning that this side wouldn't be 0, but there are still other values of sign or other values that the sign of them will still give you 0. So you have to go and look for those values. Okay, so I hope you understand now. I hope that clears the confusion, because I thought of it that maybe you may be confused, so I had to just come and also talk about that one as well. So here a is not equal to 0. This will imply that the sign of 2 pi square root of lambda should actually be equal to 0. And with this, we said that we've already known this, that the sine inverse of 0 is actually equal to n pi, where an n equals 1, 2, 3, and the rest. Since you can't even have lambda equals 0 here, because lambda is actually greater than 0. Okay, so now if I do my simplification, clearly I have my lambda being equal to n squared over 4 again. Okay, with n equals 1, 2, 3, and the rest. But remember, we've already said that, or we've already found out from this argument or this condition that b is equal to 0. So you go back to your y of x, your original y of x, and put b equals 0 there and maintain your a. So you have a cos of square root of lambda x and plus the b, but the b sign something, the b is what? 0, so you don't write that back, and this will be equal to a cos of n over 2 x. Okay, so here the eigenfunctions, okay, for the case 1. So for case 1, what we just considered, the eigenvalues are lambda n, okay, equals n squared over 4, n equals 1, 2, and the rest. And the corresponding eigenfunctions, yn of x, I said you have to take your constant to be equal to 1. So you have cos of n over 2x with n equals 1 and the rest. Okay, now you go to the another case, the case 2, and then I will leave the case 3 for you to go and do. Lambda is equal to 0. When lambda is equal to 0, we have our solution R12 will be equal to 0, that is repeated root, and I said the solution to this is written as a plus bs. And now we have that y prime, you have to find y prime of x. So y prime of x is equal to b. And you know that y of 0, or y prime of 0 is equal to 0. And this means that whenever you see x in terms of y prime, you have to put 0 there, okay? But in terms of y prime, there is no x. So 0 is equal to b, because if there was an x inside, you have to, or you're supposed to put the 0 in place of x, but there is no x. So what you have to do is just equate the function, or the function evaluated at 0 should give you 0. So the function is b. So b of 0 or y of 0 is still b. Y of everything, this is a constant function. So y prime of everything will still give you the b, okay? So y prime of 0 is supposed to be b, meaning b is 0. Also, y prime of 2 pi is supposed to be equal to 0. But you evaluate this at 2 pi, you still get b. Again, you have 0 equals b as well. And these and this are the same. And indeed, it proves that b is equal to 0. meaning that our function y of x, we've accepted the two boundary conditions, so our function y of x is equal to a for the case where lambda equals 0. So this is what you have, and that with this, the eigenvalue here, because we didn't have the trivial solution, we have a constant function y of x equals a. So here the eigenvalues lambda naught, okay, because we have only one eigenvalue, was equal to 0, and that gave an eigenfunction y naught of x being equal to 1, because I said you have to take the constant a to be equal to 1. That is what I said first. Okay, so I'll urge you to go and then search for the case 3. But in any case, the case 3 wouldn't give you any eigenvalue and eigenfunction where lambda, okay, where lambda is actually less than 0. That would bring the quotient signs. But remember, like I said, you wouldn't get any eigenfunction and eigenvalues. So in all, the solution to this is that you have this. After everything, the eigenfunctions to this question is given by eigenvalues. So you have lambda n being equal to n squared over 4 with the corresponding eigenfunction to be yn of x being equal to cos of n over 2x, with n being equal to 1, 2, 3, and the rest. Okay, and that with another eigenvalue lambda naught, which is equal to 0, with an eigenfunction y naught of x being equal to 1. But you can merge these two, okay? You can merge these two as well. That you can say, okay, the eigenvalues will still be n squared over 4, and the eigenfunctions will still be the cos of n over 2x, okay, and your n will have to define. So this is the first part, is when you are combining the two of them, but I'm merging them using the idea of cos, okay, because 0 is 1, so n start from 0, 1, 2, and the rest. And now if you use this one, you have to be able to generate all the first eigenvalues and eigenfunctions, including or together with the second set, that is the lambda naught equals 0. So when n equals 0, you have lambda naught, and you have 0 squared over 4, which is 0, and that you have y naught of x, that will be equal to cos of 0, which is 1. So you still get back this, okay? And when y or lambda n equals 1, then you start getting these ones, okay, the ones at the top. I hope you understood this. So this is all about eigenvalues and eigenfunctions of an ODE. Remember, we actually took a very simple example just for us to understand. That is this one. But you can get a different form. You can get the general form, and then you'll be asked to find the eigenvalues and eigenfunctions. In any case, you are just looking for the values of lambda that will make this function, not giving us the trivial solution. So just remember your techniques in solving equations. That is what you are supposed to get. And also with the trig functions, know their periods, their points at the points where they give values like 0 and the rest, okay? So of course, if you remember in the sign, all of them give us sign. When you have a solution that has cos of something equals 0, and you want to find the cos inverse of that, then you have to equate whatever. Let me use another page to explain what I have. If you have cos of a certain argument, okay, let's say cos of, let's say k, I'm just representing all the arguments. You can get 2 pi square root of lambda, or maybe 2 pi something, okay, equals 0. And you want to find the argument of this, then the cos inverse of 0, k, should be equal to n pi. Is it n pi? I said the sign is the n pi over 2. Sorry, n pi, but then with the cos, it's supposed to be n pi over 2. Yes, n pi over 2, where n is an odd number. Okay, so n should be like 1, 3, 5, 7, and the rest. Okay, so in any case, when you're solving eigenvalues, eigenfunction problem, and you get a cos, always remember this. Okay, the cos inverse of, so you equate whatever that is here to the cos inverse of 0, and the cos inverse of 0 is actually n pi over 2, where n is odd. So you have, when n is 1, you have cos of 90, that is 0, okay? When the n is 3, you have cos of 3 pi over 2, which is cos of 270, and that is also 0. When n is 5, you have cos of 5 pi over 2, so remember these. With the sine of pi is also 0 as well. I think the sine is also, the tangent is also the same as the sine, okay? That one too is n pi, okay? So just know these. Now I have a trial for you to go and try for me. I have y prime prime plus lambda y equals 0. With these boundary conditions, y of minus pi is the same as y of pi. Y prime of minus pi is the same as y of pi. Wow. So you have to work hard. Hence, know that the conditions remember, when you are solving, you get, I'm just giving hints here, you get the first equation to be a constant times some function equals 0. Don't equate the constant yet to 0, because how do I call it? It's coming from these conditions, and it doesn't necessarily give you any other idea that this is equal to 0. Okay, we are saying that this is supposed to be equal to something. This is equal to this. Okay, so when you get to that point, don't equate the constant to 0 yet, or equate the function to 0, because it can be this is equal to 0 or that is equal to 0. Then you consider the other case. The other case will also give you an equation in terms of the constant b. So if you equate both constant to be 0, then it means you have the trivial solution. But in any case, you still have, I think, sine, or maybe, I don't know, you still have sine to be equal to something. That is for the case 1. And also, this is your general solution. This is the general solution you get. And I've written the eigenvalues here, okay, the nx. These ones will be your eigenfunctions. And I've said that if you have a general, this is what, after solving for your eigenvalues and putting them back, none of the equations for the case 1 will go. None of the terms will go. You still have your a cos something there, b plus b cos sine something there, because the constants shouldn't be 0, and then when they are not 0, you have this. And you have a summation like this, then the eigenfunctions can be split into two, this part and this part. That's the first eigenfunction is this, and second eigenfunction is that. Now this is the solution. The answer is the eigenfunction for the case 1 will give you these two. They will give you n squared, that's the eigenvalues, n squared and n squared. And then the eigenfunctions will be the separated one. That's where I said you have to split them. Sine of nx and cos of nx. With these, n equals 1, 2, 3, and the rest. And then the case 2, where lambda should be equal to 0, this is what you get. And with the case 3, you won't get any eigenfunction and eigenvalues. But you can merge these two and say that, okay, with the case 1, that's the whole of this is case 1. They will give you n squared and sine and then cos. Okay, but the case 2 has lambda equals 0 and then y not to be equal to 1. But you can make that one with a cos, okay, because the cos of 0 is 1. So you can say that, okay, with the cos aspect, let's start n to be equal to 0 and then 1 going. Remember, here it was n equals 1 and 2, and going to 3 and the rest. But then with this one, we have n equals 0, 1, 2, 3, and the rest. I hope you understand. So this part will actually give you the second case back. Okay, so just go through it and let me know if you're able to solve it in the comment section. If you were not, then I'll have to probably send you a typed solution, or maybe there's a solution to you. Okay, I hope you understand it. Thank you, and please kindly subscribe. If you have not subscribed to my channel, just subscribe to my channel for me. Okay, help others to also benefit by sharing, liking, and also commenting as well. Thank you, and see you next time.